Hi everyone, welcome to join Innovating to TechTalk. Today we are happy to have Dr. Zhiqing Chu, Assistant Professor from Department of Electrical and Electronic Engineering and School of Biomedical Science to be our moderator. Without further ado, Professor Zhu, please.
Okay. Can you hear me? Okay. Good afternoon, everyone. Dear audience. So this Tech Talk series is a forum and a dialogue given by the engineering researchers of diverse academic backgrounds to share their insights on innovation-related topics. So today we are honored to have the speaker, Dr. Wong here. And I think I don't want to, speak a lot on behalf of him for introducing his background. So I will just pass the time to him, and I think that will be much better. Thanks.
Okay, thank you. Thank you, everyone. Can you hear me clearly? All right, great. Well, I made a sexy title, and I should admit that I'm kind of cheating in that sense because this title is not what I've been doing. You know what? My former advisor, postdoc advisor, told me the best way to learn something is to teach it, and so I'm using this occasion to also force myself to learn what is neural tangent kernel, which will be the theme for today. So to give you some perspective, in the next 5 years, I'll be doing a lot of AI chip design. So that's on the hardware side. And then while I'm looking at the next-gen AI chip design, there's something I found that we need to solve, particularly in the training of the AI. Because if we have been doing AI, the training of the network takes a lot of time. Well, let me just get into the talk, and I will just roll this out bit by bit. So the first thing I want to emphasize is that everyday life now is filled with AI. Okay, if you look at the Hong Kong U logo here, there's AI in it, which is highlighted in magenta. All right. So can you find another AI? Well, it's in my name. Okay, it's just joking. And I'm not just doing AI because you see NG preceding AI, which stands for next generation AI. So this is actually what I'm going to talk about. So when you look at the growth of the semiconductor market, it's been growing exponentially. And then this is actually a forecast by McKinsey saying that 2025, well, nowadays we have recessions and also the war, but I think it's going to taper off a little bit, but then the growth will just keep going. So if you look at the fine print here, AI circuit versus non-AI circuit. Non-AI is the lion's share here, but then the growth of the AI component is 5 times that of the non-AI. Okay, so that is evidence that AI is penetrating into our everyday life. So the hype, the wave of AI started in 2016, and it was this game was very well known. It's a game between AlphaGo and also Lisedo, and then human lost the game. So that sent a short wave through the community about the power of AI. So do you think it's really the triumph of deep learning? Would deep learning overtake human in every aspect? Of course, I will put a big question mark here. Because if you look at the power bill behind, the human brain at its peak is burning 20 watts only. But then the AlphaGo was making use of more than 1,000 CPU, 176 GPU, and then the wattage is a lot of zeros. Okay, so in order to match with the human kind of order of wattage, we have to cut at least 1,000 times. Right, so that put me into the, I set my goal of doing AI chip that can achieve at least this 1,000 time reduction in power. So I look at the trend of nowadays technology and observe 2 shifts in the computing paradigm. One is that we still have the data center doing a lot of heavy lifting work, but then a lot of the tasks now they are loaded to our edge devices, such as our cell phone, our smartwatch, and so on. And then there's another less obvious, subtle change is that we used to have von Neumann architecture in our computer, meaning that the processing element and the memory, they are separate. So a lot of energy are wasted in just moving the data around. So another shift that I want to draw attention to is that nowadays we are looking, we are seeing more and more products that emphasize on the near memory computing or take it to the extreme, the in-memory computing. So these kind of devices have very low power, low latency, high speed, and so on. But then it's usually constrained in terms of storage and also compute. So I wonder if any one of you is a fan of Japanese anime. So do you recognize this scene? It's from the anime called Attack on Titans, okay? Do you know the name of that big giants over there? It's called the Colossal Titan, very big Titan. So I want to use this picture to analogize the different sizes of AI model. For example, I can name this GPT-3. Probably you know that this is a language model. Number of parameters in this is 175 billion, and storage is 800 gigabytes plus, all right? Versus, we also have small size AI model. We call it the Edge AI. An example would be MCUNet, okay? You can buy off-the-shelf MCU at 10 US dollar and something. And the number of parameters of the model that you can fit on it would be 256, and then storage is less than 1 megabyte. But then you can still do face recognition and even wake word recognition. So it is still as powerful, just that it cannot run very sophisticated model like the language model. So, and indeed, there is another website, tinyml.org, that talks about this organization focusing on the research of edge AI or edge computing. And well, by coincidence, there will be a Asia-based symposium coming up, and you can register online because it's going to take place by the end of this month. So take note of that. This indeed quite exciting. And in fact, I'm not presenting that there will be colleagues from other universities, but this is a worth attending. So I want to take you now. First of all, the theme that I want to set up would be, we want to focus on edge AI. And because we do it on the edge, we cannot do heavy lifting training because it takes hours of GPU time, a lot of power. So we want to go simple. And this it aligns with what the title for today, want to do machine learning without the learning. So I set the prerequisite to be like this. We have to have some basic understanding of linear algebra and less basic understanding of linear algebra, namely the matrix calculus. And then, but then, even if you don't know this, never mind. As long as you have open mind imagination, you can still grab something from this talk. And in case you want to get a grasp of the matrix knowledge, you can attend my year 1 course, which I'm teaching math 1863. So that's a privilege for Hong Kong U students here. So I want to start with something really simple. Let's say I have a lot of data points here. The red stands for the positive, blue stands for the negative. I want you to classify them. So mathematically, this is a Cartesian plane. So the classifier that you immediately pop up in your mind will be a line, right? So this line can be described as a row vector multiplied with a data point, okay? So this line is said to be 0 that cuts through the origin in this simple example. So whenever this y, we call it the label, overshoot 0 into positive, we call it a yes. And if it undershoots 0 into negative, then it is a no. So we can mathematically describe a binary classifier. Okay, so this is x1, x2 here stand for just one data point. So suppose you have a lot of training data point, we call it the support or the sample data point, then we can fit it into a so-called least square matrix equation like this. What we want to train here will be this W transpose, a row vector. When we fit it with a lot of training sample, for example, this XS1 means the first sample, and then YS1 is the first label, and then we have a bunch of sample, a bunch of label. We set up a matrix equation like this. So if you have been to my course, what's the next step? Next step, intuitively, because the XS, which is the sample matrix, is a fat matrix. So next thing you want to do is to multiply the transpose of it. So you have XS transpose, which is square matrix. And because this is square, let's assume it is full rank. So we can do the inversion to the left-hand side to find this W transpose. Now here I pop up a so-called representative theorem. It is related to a Chinese poetry saying that, well, what is the optimal W here? The W would be a linear combination of the data sample, meaning that the optimal W that draw the classifier, the classifying line, would be something, a mix of your input data sample, okay? So that's called the representative theorem. So bearing this in mind, we have computed the row linear classifier, the WT, from the set of training sample. And then we can use this WT to classify unseen data before. So I call it the target or the test data. So we have a bunch of test data coming in, and the classifier would then spit out a bunch of label, okay, corresponding to this classifier based on the knowledge it learned from the sample or the support training data, okay? So this is a linear case. Now I want to turn to another question to guide you into an understanding of the neural network. Suppose I have Mars alien, which is a total stranger to us, and also assume each of this Mars alien would have a favorite Earth object, okay? We don't know what this object is, but we can ask it yes, no question. So let's start with the first question. Do you like animal? The answer, no, okay? Next, building, Hong Kong U, Inner Wing, 2, no. And then how about fruit? The answer turns out to be yes. So we narrow down our search scope to the bunch of fruit. And then is it red in color? No. Yellow? Yes. Round? No. Long? Yes. Bent? Yes. So can you guess what fruit is it? Banana, right? Okay, good. So this kind of mapping can be represented as a bunch of classifier, okay? And then by asking many enough questions, we can get to the answer. So we can develop a mapping by asking a series of questions. And this is exactly what a one hidden layer, let's talk about it later. So this is the look for a neural network. So we can ask it in a hierarchical way. Nature, okay? Color, and then shape, okay? So this is a deep neural network. So neural network 101 is exactly like this. So back to our line drawing problem before. Remember in the previous case, we were able to draw a straight line through to do the classification quite easily. But now these points are messed up. So can we still draw one line to cut them into red and blue? No longer so easy, right? But it's not undoable, okay? It's not impossible. What we can do is to do a so-called feature mapping. We can project it onto a high dimensional space. So let's say I define my phi function to be something like this. So it is only one dimension higher, but then I'm already able to spread them out in the 3D space, okay? And then I can cut through using a hyperplane, still separating the red from the blue. So projecting to a high dimensional so-called feature space does give us some advantage and niche in separating or classifying the data. So let's say I have a lot of, now still the same old case, training sample, but now I project it to a very high dimension, okay, using this phi function. So still the same old problem as before, but you can imagine that these are very, very tall vectors, very long, can be infinitely long. So we are designing a infinitely wide W to do the classification for us. But making use of the representative theorem, I know that I have the prior knowledge that this W would be a span or a mix of the data sample, okay, of the training sample. So I recast my W into a linear combination of this training sample with the combination with the coefficient alpha here. And then I plug in this W into here. And you can see that immediately this phi here are doing a lot of row column multiplication, eventually giving us this so-called kernel matrix or gram matrix, okay? So this matrix is known based on the training data. And then having known this KS, I plug it in and then do the inversion to the left-hand side, more or less like before. And then I can come up with a determined solution for this W. Remember, I said this phi here can be extremely tall or even infinitely tall. But what we really care is the inner product between two tall vectors. So we never need to compute it explicitly. Rather, we want to come up with a so-called kernel function that can allow us, this is so-called kernel trick, that can allow us to compute the inner product of the very long vector in this sense. Okay, so can you give me, I mean, I'm asking myself, can I give a example for this kernel? So this is a very well-known kernel, sometimes known as the Gaussian kernel. It's based on the exponential function, which has a so-called Taylor series expansion like this. So if I plug in two vectors, if I define my kernel here to be two vectors like this, I plug in to this RBF or Gaussian kernel, then I can expand it into an infinitely long polynomial series, and it will mimic the inner product between two infinitely long vectors. Okay, so this is the so-called kernel trick. Although it is a projection or inner product between two infinitely long vectors, I never needed to compute it explicitly. Rather, I'll compute it in a very low dimensional domain. Okay, so this is the kernel trick that we build on, and this is called the Taylor series expansion. Okay, so Taylor series expansion is like we pick a point where we do the expansion by doing some differentiation, and we'll come back to it later on. So now back to the design of the neural network. I don't want to train it, but I want to give you a sense of what a deep neural network would be like. And this is the basic type of neural network, which we call the MLP, multi-layer perceptron or fully connected layer neural network. So you start, there's some stranger symbol here, but never mind. It means it is a real number dimension D, which is the input, okay? And then we just have this kind of so-called hidden layer. So H tilde here will be a linear mapping from the input end, and then it will go through this red neuron here, which are nonlinearity function or nonlinear activation, resulting in H without the tilde. And then after some layers, eventually I get my output, the Fx. The theta here is a holder for all the network parameters here. So it is a very bulky network. I have to, if you do neural network training, then you send it to GPU, use the so-called SGD, stochastic gradient descent, a lot of training data to train it in minutes or even hours or days, okay? So it takes a lot of time. So my question here is, can I come up with a set of theta which is good enough and doesn't require any training? So for better visualization, we look at a two hidden layer neural network, and it's undergoing training. As you can see, if I have a not so wide neural network, it is an animated GIF, and it is moving. So when the training is going on, but when you look at the M100 and M1000 case, they are animated GIF, they are realistic animated GIF, but essentially you don't see any changes over there. Okay. So this is a phenomenon called lazy training. You do not need to look at it. I've looked at it long enough and not able to observe any changes. But frankly, these are animated GIFs. So the reason behind is actually very simple. Because all these neurons are being trained to exercise their force to turn the output into something. If now you have a lot of neurons, a lot of connection here, then each of them will bear a very light load, right? So if we have 100 people moving something, it will be extremely easy rather than 10 people moving something heavy, okay? So that is what is called lazy training. So the take-home message here is, if we have a lot of neural links like this, if we have a lot of weight parameter, then the neural network, even it is randomly initialized, once you train it, it doesn't really change, okay? It doesn't really matter where you initialize it. So at this point, something not changing, or something changing only very, with a very tiny portion, we can do Taylor series expansion. Now I want to relate these two diagrams. What we want to train would be the theta. Theta is holding all this weight parameter here, okay? And then by lazy training, I know that this weight parameter, even when you train them, they do not really change, or they change in a very minute manner. They change only infinitesimally small. So what we can do is we grab all these parameter into a theta vector, and then this is a terrace. Okay, this is a landscape that I want to analogize to the training. So I want to hit the low point. I know that when it is very wide, it is a bulky network, and when I initialize it randomly, I'm going to hit the lowest point somehow, okay? And around this lower point, I have now this is a symbol for gradient. I have a very flat plateau over here, and then it is a whole basin, okay? No matter where I initialize it, it's okay because it's hitting near optimal. And then I'm going to do my Taylor series expansion on that. Remember, from day one, what we want to do, I want to learn the theta, okay? I want to learn theta. And when the theta is very, very long, I don't really need to change it, okay? So keep this in mind. And because it doesn't really change around the optimal point, so I can approximate it well with a first order Taylor series expansion like this. And what we want to learn at the end will be this set of theta. So how can I do the projection to the high dimensional space? Bravo. Here you go. If I have an input x, if I compute the gradient of f with respect to theta, it's like carrying the x to a very, very high dimension. Okay. So if you look at this first order Taylor series expansion, does it ring a bell? Have you seen it somewhere else? Yes. Look at this. This is something very long. And theta is something that we are going to design. And we have the label for training that. And this takes us by time machine, we travel back a few slides. It's something that is similar exactly to the case here. We have some very long vector. W is something that we are training, and we have the train label, an input data set for that. So coming back here, I have very long lifted feature vector initiated by all these train sample. And these are very long, or even infinitely long vectors. Okay. And I want to train the theta of it. And we already know the trick for doing that. What we want to do is to compute the kernel function, okay, which is the inner product between two very long vectors. So how can I compute this kernel function? This is the so-called neural tangent kernel. But before we move on to neural tangent kernel, there's a predecessor knowledge that we need to pick up, which is called the neural network Gaussian process. What it does is, now here, this neural network is deep and very wide, and then the output is taken from a very deep layer. But how do I train it? Let's not, there are some strange symbol here again, but never mind, this is expectation, okay? It stands for expectation. It means that if I stand at early layer, I don't really need to go deep in the first place. I start from layer 1. I stand at right before this web ball here. There's a bunch of recursive relationships that govern the behavior of this ball. At this ball here, I'm looking at the expectation or the covariance of its output subject to two different input samples. Okay. Well, very deep, but never mind. Once again, if I fit a lot of X in it and I look at the correlation when I stand, let's say I stand at this red yellow ball here, okay? I look at the distribution of the output. It is Gaussian, meaning that it follows a bell shape, an inverted bell shape. So it is Gaussian, and it is indeed this expression here, if I stand at the first ball. So knowing that, now, by the way, every red neuron inside this first layer will see the same expression, okay? So this is mathematically provable. And then after knowing the first layer's expression here, I can move on to the second layer, and I build a covariant matrix. At the second layer, I sample something from here, and then I can have another so-called NNGP kernel or covariance. So by doing this, eventually I get to the end. So this is very complex, put you into sleep immediately, but somebody has been kind enough, actually a bunch of researchers from Google, that has computed the NNGP kernel function for us. And assuming that this is ReLU activation, very popular activation, we do have a closed form, an analytical form for the K function here. So this mimic the inner product between two infinitely long vectors here. So knowing this NNGP kernel or covariant function, what we can do is to really set up the NTK for it. Okay, so this is expectation symbol. So this is NTK. We have set our goal to find the inner product between two very long gradient vector. That would be our NTK. So the NTK is very closely related to NNGP. So I don't bother to derive it. I just give you the end result. So the NTK is dependent on the NNGP, neural network Gaussian process, again, recursively. So we can go from the first layer and then eventually travel to the output layer and get that NTK function. And again, for the popular activation function value, we do have a closed form NTK kernel function for it. So this is NTK. So at this point, I know a lot of you will have this expression, but never mind. The take-home message is infinitely wide DNN trained by gradient descent is exactly equivalent to kernel regression via the NTK. Okay, so we don't really need to train it because we can skip all the training and describe its behavior using this NTK. So as I mentioned, Google's team has done the heavy lifting for us in coming up with the new tangent library. It's developed by Google, and everybody is free to use it. It's open sourced. And then what it does is you can mess with a lot of neural architecture. You can build a network, finite width neural network, and then the library will tell you what the kernel function would be in the NTK regime. And they list a set of supported activation and neural architecture. And it is as simple as calling a few API. My PhD will, Jason will do some demo for us later on. So I haven't done publication in NTK yet, but we did some prior experiment to validate that it is also practically useful. In one of the application scenario, people in the past used to use finite width MLP. They train it using the coordinate input and then the corresponding RGB output, and then build a new a MLP for it. And this kind of coordinate-based MLP is used in scene, 3D scene description, occupancy network, MRI reconstruction, and a lot of things. So training this thing can take us a long time, okay, in terms of minutes or up to hours. But what we can do with NTK, which has not been done by other people yet, but we have done it, is that we use the NT library, use some in-house trick that I'm not going to disclose here, but it is all analytic. And we can show that it can readily overtake all the tensor or matrix compression algorithm out there. Okay, using NTK, we are able to overtake all sort of image compression algorithm based on tensor and matrix algebra. And here you can hardly even see the picture because the ground truth picture is a fox head, right? We dump 99% of pixel, retaining only 1%. And we apply NTK, coordinate-based MLP, to do the reconstruction of the fox head. And you can still vaguely observe that this is a fox head, okay? So this is extremely magical. And we can, apart from doing reconstruction, we can do super resolution because it can interpolate the missing point quite nicely over superior to all tensor-based compression algorithm. And there are a lot more applications that we can actually employ or deploy on top of the NTK framework. So the limitation, of course, there's no free lunch. And we have to compute this kernel matrix and then do an inversion of it. So this is extremely storage demanding. Okay, when we have a lot of training sample, even for a picture of size 512, 512, is a lot of training sample already. And we have to do the inversion of that matrix. So this is, again, another heavy burden for NTK. And it simply cannot deal with high resolution images, okay, the traditional way. If you want to do it the standard way, sorry, that's not doable, okay? It is prohibitively computationally heavy. But of course, our group has a trick of overcoming this hurdle to do it, which we will be reporting in some work later on. So if you want to join the hop on the wagon of doing NTK research, you're welcome to look at this online course from MIT. And think the slide can be shared later on. So you can check this out. It has a bunch of very nicely made YouTube video and then some notes. And then if it is too long to read, you want to have a quick version or quick crash course on NTK, then these are two blogs that I find particularly useful. But mind you that all this material here, as well as these two blogs, they contain a lot of bugs in math, okay? So far, I haven't seen one website that capture all the math accurately and error-free. So there are a lot of hidden devil inside the map. So you have to pay the effort of really working out all the math if you really want to jump into it. So that's the end of my talk. So the take home is training infinitely wide neural network by gradient descent is exactly just NTK regression. We really do not need any training because the network can be computed analytically. And then later on, I'm going to ask my PhD, Jason, to do some demo, and then I can take questions from all of you. Okay, so Jason, your turn. Thank you.
So hi, so in the following 5 minutes, I will show some simple demos using the NT library, which is developed by Google. So let's install and import the library. So we are using the neural tangent library. Some setup code. So the first demo I'm going to show is to do a simple 1D regression task. So here I'm trying to fetch data from the Hong Kong observatory using their open API. So here is the mean temperature for the 2022 in Hong Kong. So the blue one is the ground truth, which is the correct data, and the red cross is the data I used to train the NTK. So we are trying to interpolate the point in between. Actually, there's no explicit training as explained by Dr. Wong. We are computing the analytical solution for the predictor. So here you can see the blue curve are the interpolate result from the NTK. You can see it's quite easy to use, just few lines of code and you can already use it. So it's a quite good off-the-shelf machine learning predictor, and you can use it for any regression task. So for the second task, I'm extending this to the 2D scenario. We are doing a 2D regression. So here we will first take a picture. So let's take a picture of the audience. So this is the image we are going to use. And similar to the Fox image that presented by Dr. Wong, we try to sample only 15% of the pixel from this image. So you can hardly see what's in the picture. So our goal is to try to reconstruct this image. So we are also using the NTK, but in this scenario, we are doing a 2D regression task. So we can see the training is very fast. and already reconstructing the image. So we take 10 seconds. So here is the result. So on the right, on your right hand side is the image we used to train the NTK, and you can see is the reconstructed image. So you can see that NTK is quite powerful in the sense without any training, it can already pick some pattern from this image with only a very few pixels. So yeah, I think I finished the demo.
Okay, thank you. So if you were following, the training actually takes no time. Most of the time is spent on inferencing, meaning that you remember there's a neural network behind. So we input the coordinate, asking or querying the network what the output RGB value is. So most of the time is spent on asking the neural network what pixel RGB value should that pixel have. Okay, so and then it does a raster scan throughout this picture and doing all those inferencing. So it is so inferencing is the workload for generating this picture rather than the training. So this is in contrary to the usual practice of neural network learning, in which we spend hours on the training and then inferencing is just a split second. So that shows the niche of understanding NTK and making good use of it. Okay, so that will conclude the talk today, and I welcome any question you may have.